Just take a few seconds to help everyone join in. Okay, so under mechanical properties of metals, we're going to look at the properties that make metals what they are, or generally materials anyway. Actually, here it's not just metals we look at, but we'll look a bit at polymers also and ceramics also, and try and understand what makes ceramics, okay, and what makes metals, what makes them unique, what are the features that they have, okay, that are naturally occurring that make them attractive to us. Okay, well, that make them maybe in terms of looking for a hard material, in terms of hardness, in terms of malleability. So what makes metals, for example, malleable? What makes them hard? And so on and so forth. So we're going to look at those properties and just try and understand them and how we use them to our advantage in industry. We'll also look at testing. Actually, we're going to start by looking at testing, materials testing, which is tensile testing. Can we please mute our mics for now? Okay, so this is the various, this is part of the equipment that we use in the lab, okay, for metals testing or for materials testing. This is also part of it. You can see this gentleman standing here and trying to do something there. So for civil engineers, of course, they do a lot of testing of the concrete and the whatnot. They have like a wider range of tests that they do on the materials that are used for building. Okay, they're always testing for strength, especially tensile strength is very, very important in the construction of bridges. Okay, in the construction of buildings. Was it this group that I sent a video? Okay, so I don't know, probably you've seen it on Facebook where, you know, a group of, I think usually African countries, they'll be commissioning a small bridge, then the bridge collapses before the minister even cuts the ribbon or in the air. So what leads to that? Why are bridges collapsing even before they're commissioned, or right on commissioning day? Before the minister is just like 1 second away from cutting the ribbon, and then his legs are in the air because of poor material choice or material selection. So material selection is very, very important in any construction project that is undertaken. Very, very important for you to, can we please mute our mics? Very, very important for us to pick the right material, okay? Because if we don't pick the right material, we are going to end up forming a disaster, okay? Because we end up picking materials that will not sustain the pressure coming from the required pressure, or I'll put it that way for now. Okay, so it's very, very important, and that is where you come in. That is where you come in also as personnel that will be working. Madam Charity, please, can you kindly mute your mic? That's where you come in now, okay, under purchasing and supply, because you are the one who's going to be doing this purchasing. Various orders will be coming to your department, procurement department, to be purchased. What is that word again? Is it purchase officers? What's the title? Please correct me where I'm wrong on the title. Procurement, is it procurement officer? It's procurement officers, isn't it? Everyone is quiet. Am I saying the right thing or not? I need feedback from you.
Yeah, you're right, madam.
Yes, madam. Procurement officers. So are you currently working as procurement officers?
Yes, madam, we are.
Okay. All right. So you know at least. So what procurement usually are you doing? To do with materials.
It's somehow general, madam.
Okay.
It is not specific per se. Of course, most of the times it has to be one where, depending on the items that you're about to buy. If it is those that require expert advice or maybe a touch of expertise, means you have to involve the people that are experts in that item so that even as you buy, themselves as the people to use that item know to say this is the right one for this type of maybe duty or purpose.
Okay. But you should also give a guide, isn't it?
Yes, madam, we do.
You also guide, isn't it? Okay. So I guess that's why
Yes, madam.
this particular course is important for you to understand materials. Okay, because you should be able to guide the type of steel, maybe that is hard or that is required for that particular job. At least if you understand steels, okay, and their codes and which ones are necessary and which ones are not, that would be better for you. Okay, so maybe my examples will usually incline towards the mining sector because I'm an engineer myself and I'm closer to the mining sector. But I guess the understanding will still be the same. So in the case where you have been asked, you know, if an order comes to you for certain materials, okay, so it's much more difficult if you do not even know, okay, the difference, okay, between these materials, what is best. It will be hard for you to even know when there's some malpractice going on, for example. Okay, so it's always best for you to have that knowledge, to have the basic knowledge. Even in terms of storage, okay, you need to know which materials should be stored next to which ones in your storage facility. That at least that knowledge is expected to come from you. Unless maybe you hire engineers to come and arrange stuff in your storeroom for you, but generally you should be able to have that basic understanding of materials and how they react, which ones react with one another, and so on and so forth. I know they'll come with their various instructions, but basically that's the knowledge that you need. So you need to have some working knowledge at least of that. So look at this bridge, a very famous bridge in the United States. I've forgotten what it's called. Very beautiful art of engineering. Okay, this is a marvel of engineering, and it's admired by many. Okay, so you have the cars there running down, tiny cars. So what looks like decorations actually is somehow aiding in the support, okay, of this bridge. So a lot of calculation went into this construction. A lot of calculations were done, a lot of tests were done on the materials. They just didn't wake up and say, okay, let's try this kind of steel, for example. No. So everything was carefully thought through. And the knowledge they had is the knowledge that you're also going to acquire at the end of this course. And maybe they probably had a bit more, but at least the basic knowledge is exactly what you are also going to have here. So you for tests for before you pick the material, you need to get specimen, okay, different types of materials, and test them. Okay, if you don't have that prior knowledge, test them in your lab or have them tested elsewhere. For example, for strength or for other properties, have them tested, and then you choose your desired level of strength depending on your project. Okay, so under design and manufacturing, you have the physical properties there, isn't it, that are considered mechanical. So under physical properties, this is a general method to differentiate materials using what density, melting point. Okay, so for density, for example, if you know that this is copper, density of copper will always be the same. One moment. So for example, density of material will always be the same. Okay, these are just, these are tables at the back of the textbook that do not change. Melting points, okay, will always be the same, at least almost the same. Just like water, isn't it? Water will boil at similar temperatures, whether in Europe or elsewhere or in Africa, it boils in the same temperature range, very close temperature range, and freezes at a very similar temperature range. Okay, so optical properties, transparency or opaqueness, those ones you can actually, there's a test for that one also. Electrical conductivity also we have, those are already defined, okay. Every material has its own defined electrical conductivity. Copper has its own electrical conductivity and so on and so forth. So coming to mechanical properties, these ones determine a material's behavior when subjected to mechanical stresses or load or forces. So now this is how does, okay, so when we're conducting mechanical properties, we're trying to understand how does this material behave when it's subjected to certain stresses or load or forces or temperatures. Okay, so the properties that we're looking for there include elastic modulus, the ductility, we're looking at hardness, and other measures of strength. Okay, so how do you determine a material's behavior? Very simple. Let's say you want to try a polymer in the kitchen, and you tell yourself, okay, how does this polymer behave under high temperatures? Let's say temperature of 110 degrees Celsius. You get that container or plastic bottle and place it on your stove and switch on the stove, the plate of the stove, and it will begin to melt right away. So that would be it would begin to melt slowly, and that will tell you the behavior of that particular material when it's subjected to temperatures. So there'll be a certain temperature when it will begin to melt. There's a certain temperature that to tolerate, okay, after which it will begin to melt. So it would have reached its melting point. So you would have known the melting point for that particular type of polymer. That's an example. So mechanical property is desirable to the designer. So who's the designer here? The designer is a person who's been assigned to come up with a design for equipment or infrastructure, okay, such as a bridge, okay, or maybe it's a machine, even a car, okay. So it begins at design stage. So all projects have to begin at first the concept, then the design now comes in, or concept and design together. So the designer has to work hand in hand with the manufacturer, because the designer has to design something that is workable, okay, something that is realistic enough to be handled by the manufacturer. So if the designer, comes up with something that is unrealistic, then it's hard for the manufacturer to actually replicate this design, okay, or to come up with an artifact or an object out of what the designer has put across or has laid on paper. So these two have to always collaborate. So mechanical properties desirable to the designer, such as high strength, usually make manufacturing more difficult. The manufacturing engineer should appreciate the design viewpoint, and the designer should be aware of the manufacturing viewpoint. Same with house construction. Everyone has their dream house and how they want it to look like. But sometimes, you may have been dreaming of a certain design of a house for years and years. You want the swimming pool to be on top of the whatnot, I don't know what, on the third floor, and then you want something, something just, something that in your dreams, it actually, when you close your eyes, you even see the house, you even be walking around it. But when you take your ideas to the architect, you will not be able to replicate that, okay, because there are certain things, okay, standards that have to be maintained, okay, in any design, and he may not be able to, or even if he did, okay, the bricklayers won't be able to construct things the way you want them to, because there are certain things and certain, especially when it comes to do with strength, that's where usually the issue is, the bone of contention is. So all parties have to be involved, and there has to be some general understanding of everything. Okay, so even in the construction of an airplane, okay, design has to come in place. And then from the design stage, now it goes to the manufacturer stage, where the manufacturer now comes up with this object that was designed or drawn by the designer. So a plane does not look like this. because someone just felt it looked beautiful. Okay, there's a lot of considerations that came. Okay, of course, the general idea is that it's supposed to replicate a bird that's flying. Okay, but still, you know, every detail, everything is not just there for just being there. There's a reason why, you know, it has these issues here, back there, and so on and so forth. Okay, and then what else is worth noting here? So key mechanical design properties are stiffness, strength, hardness, ductility, and toughness. So you need to know, at least have the definitions of each of these terms, and more, at least you need to understand, you should be able to define what stiffness is, what strength is, what hardness, ductility, toughness are. Maybe you already know actually. So materials engineers are concerned with producing and fabricating materials to meet service requirements as predicted by these stress analysis. That's the objective. So there are two types of stress or load: static or dynamic stresses. So we know what static is. Static means something that's not moving. Static stress is when forces that are applied to materials are constant, while dynamic stresses have forces changing with time. That's the difference. And static stresses to which materials can be subjected can be tensile stress. So tensile stress tends to stretch out the material. So imagine you're holding a loaf of bread. Okay, so you're holding one end on your left hand and the other end on your right hand of a piece of bread. What happens when you stretch out your hand? What happens? Provided it's not sliced, obviously. What will happen to the bread?
It will cut.
It will cut immediately or after some time?
For bread, it's supposed to be immediate, madam.
Really? It has no elasticity whatsoever.
It will stretch, madam, then it will tear.
It will stretch a bit, isn't it? I think it has some kind of elasticity.
Get cut.
Huh? So as you are provided,
Yes, madam, it has.
It has, eh? So what does this mean? It means the force that you are applying on the bread on both ends, provided the force you're applying on the left hand is equal to the force on the right hand, isn't it? That is what? That's tensile stress. So you're basically stressing that loaf of bread. Okay, you're pulling it out, stretch those are known as tensile stresses. While the compression forces, they are tensile forces, while the compression forces do the opposite. So that same piece of bread, okay, another one, okay, get another one, forget about the one you cut. Get another one, if another piece of bread, you can try this at Pick and Pay or ShopRite. Get another one and you compress it. So how are you applying forces? So from your left hand and your right hand, you bring your both hands together. What happens to the loaf of bread?
It compresses.
Compresses.
Okay, apart from the word compress, is there any other word we can use?
Shrink.
Okay, it becomes
Squeezed
smaller
in.
and it becomes squeezed in, isn't it? It kind of squeezes in.
Yeah, it
Okay.
squeezes in.
All right, so the tensile is the opposite of the compression. Do we agree?
Yes, we do.
Yes.
Okay, so
Yes.
you put that loaf of bread back on the shelf. Get a third loaf of bread now. Hold it on both ends with your hands, your left and your right hand, and then you try and apply forces, okay, in the one force going clockwise direction, the other one anti-clockwise, almost as if you're twisting the bread. Just by, let's say 30 degrees, okay, movement. at the same time, both your left and your right. So you kind of like you're twisting it, huh? Like 30 degrees, just a bit, and you stop. What happens? It will return, isn't it? Usually it will most likely to return back to its original shape, isn't it?
Yes.
But most likely, maybe let's say if you increase the degrees, it will most likely maybe come to a part where, or to a certain stage where it won't be able to return to its normal shape. Okay, the shape will become distorted. So that is known as shear. Okay, shear stress. That is the kind of understanding. It's more like a twist. You get a loaf of bread and you're holding it on both sides and you're trying to squeeze it, you twist it a bit. Okay, so what happens to the lines, the edges? So it basically means that those atoms that are placed on the edges of your loaf of bread, they become distorted. Huh? So there's some movement, some sliding movement that's going to happen. Some of those atoms, that is what we understand here under shear stress. They tend to slide a material. Okay, it comes under here. So obviously, if you're in ShopRite or you're in Pick and Pay and you're doing such things, I don't know if you manage to leave the place without being stopped. But anyway, I guess we've understood the concepts here of these stresses. So there's what is known as a very important curve known as the stress-strain curve. This is a basic relationship that describes mechanical properties for materials. So usually how I set my exams is that the compulsory question, I'll have there are two topics that I love that I usually put. So I'll usually, if it's not stress strain curve where you need a graph paper and whatnot, then it will be phase diagrams. That will be the compulsory question.
Come again, madam.
For my compulsory question in my exams, I like two topics that I pick every year. So it's either this stress strain, the stress strain curve, okay, where you have to work with graph paper. You have to draw the curve on graph. You'll be provided with graph paper in the exam. Okay, and you solve according to the formula that we look at, with the formula what we're going to look at today. Or I'll pick a question on phase diagrams. So looking at that paper that I shared with you, the past paper, I think it was it for this year? It was for this year. It had phase diagram, I think, as the compulsory question. Anyway, last year, we had the stress strain curve as the compulsory question. So this year, we're going to have phase diagrams as the compulsory question. So this particular topic will just come in as the other questions, okay? Not the compulsory question. So it will come under the other topic, but we're going to have this one in the test because when we meet, we're going to have a test just before we have the exam. Are we together?
Yes, madam.
Okay, so this topic is going to be there in test one. Okay, so we look at, so this is basically how it happens. Okay, the tensile test. Common test for studying the stress-strain relationship, especially metals. In the test, a force pulls the material, elongating it and reducing its diameter. So with a loaf of bread, as you're pulling it, okay, under tensile, as you're pulling it, you're stretching it out. As you are stretching it out, it's becoming thinner and thinner. So it doesn't just break somewhere in the middle. Okay, so the breaking will happen in the middle provided the force on the right hand and the force on the left hand are equal. So that breaking is going to happen not immediately. Okay, first what's going to happen is that it's going to thin out. Okay, it's going to become slimmer. The loaf will become slimmer just before the breaking. So that process of becoming slimmer is what is known as necking. We'll look at that further down. Okay, so what does this mean? Look at this particular specimen. Okay, and it's placed on the tensile test machine. And then forces are applied. on it. Okay, there's a force, the F going up there, okay, and the other one at the bottom, stretching it out. That is the initial diameter, A0. So what happens as you are stretching out, it's elongating, okay, it's thinning out. So as it's elongating, it means that the initial L, the initial length won't be the same as the final length, huh? Provided at this point you stop applying the forces. You find that this length and this length will be different. Okay, what else will be different? Of course, the cross-sectional diameter will be, provided this is a cylinder, cylindrical in shape. So it means that the cross-sectional diameter will also be different. It's going to be smaller. The A here final will be smaller than the cross-sectional area, which is the A0. The initial cross-sectional area, this one will be bigger than this one, obviously. Okay, let's look at it again. So there's for the specimen, of course, specimen are prepared according to standards. Okay, there are about 2 standards that are used. One of them is this one, the AST, American Society for Testing and Materials. It specifies the preparation of the test specimen. Okay, so they should have a particular diameter and the reduced section. So in short, the specimen should look like this. It has to be prepared beforehand of that particular material that you want to test. So it should look like this. Okay, that's why for many questions, you find that the gauge length will be 50 millimeters. Okay, 50 millimeters, and usually the diameter will be in this range. But of course, with testing questions, if it make it too obvious, then you know, people will just memorize this. But sometimes you find that in questions, the examiner will play around with these numbers just to confuse you. But otherwise, the standard is this. This is the standard that we usually use. This is the common standard. Those are the gauge marks, and that's where the L is. This is the machine where you have the springs. That's the machine. The specimen ends just here and over there. Okay, so coming to the tensile test setup. That's how it looks like. Okay, so that's your specimen, and those are the forces being applied, the tensile forces being applied, and that's a base. This could be placed on the table, like we saw in the earlier picture that I showed you. So how does this process happen? Okay, the tensile test sequence. So typical progress of a tensile test, beginning of the test, there's no load. Okay, this is before you put it now on the machine. So this is what you have, your L initial. Then now you begin to apply load or stress. Okay, so as you're applying those forces, okay, the tensile forces, the elongation begins to happen. Okay, that elongation begins to happen. And then after some time, over time, you begin to notice some thinning out. Okay, provided this F and this F are equal. This will happen at the center. So you have that thinning out, what is known as necking. So this is known as necking. Then after some time, what happens? It snaps. Okay, the material will snap right there in the center, and you have these separate materials. Then when you put them back, that is the length at fracture. That is known as the length at fracture. So this is determining the length, okay, of your specimen just before fracture. That is our LF that we work with a lot of times. Can you please mute our mics? Okay, so there we go. Beginning of the tests, that's number 1. Number 2, uniform elongation and reduction of cross-sectional area. Okay, that's number 2. Number 3, what happens? Continued elongation and maximum load reached. Can you please mute our mics? Okay, so number 4, necking begins, load begins to decrease. That's when necking begins. And then 5 is fracture. Okay, then when you put back these 2 materials, join them back together, get that length. This is the length that you will get just before the fracture, of the LF as it is known. Okay, the LF as it is known. So usually in the physical class, I usually like to get an elastic band, the ones that we use to tie money. Those ones, So what happens? Remember, just from childhood, we used to play with those a lot. So what would happen is that you'd stretch one and hit your friends with it. Or you would just be playing with it yourself. You hold one end with your hand and the other one on the other hand. So what's happening there? It's going to stretch, okay, for a period of time, after which it will give up and snap, okay? That's basically what happens here after some stress is applied on them. Okay, so what do we have here? The output of a tensile test is recorded, usually on a computer. So now we have the computerized tests, so the testing machines. For them, what they do is that you just simply place a specimen there and it will do the recording to even draw a graph for you. Okay, it depicts the stages of the tensile stress. And there's one general formula. Oh yeah, so one important thing here, to minimize those geometrical factors, load and elongation are normalized to the respective parameters of engineering stress and engineering strain. So there we have it. This is the formula for engineering stress. Sigma, okay, is equal to force over cross-sectional area. So now let me say this, very important. Stress is equal to force over area. Stress is equal to force over initial cross-sectional area, if you want to find the force. Force is measured in newtons per meter squared. The newtons comes from the F component, which is force, okay? Sometimes you'll be given force in terms of kilonewtons or kilopascals or megapascals or gigapascals, but bring it down to newtons per meter squared. Why the meter squared? Meter squared component comes from cross-sectional area. Area itself is meter squared, centimeter squared. So whatever it is, millimeter squared, newtons per millimeter squared, actually, this is an error. So sigma should be force over, should be newtons over millimeter squared. Okay, that's the best. Because newtons per millimeter squared will give you pascals. So 1 Newton per millimeter squared is equal to 1 Pascal. 1 megapascal, sorry. So 1 Newton per millimeter squared is equal to 1 megapascal. Usually in questions, you'll find this one to be in millimeters. Okay, this one usually is what will vary. So it's up to you. If it's in kilonewtons, you have to convert, move from kilonewtons to newtons, you divide by what? 1,000. Or you multiply by 1,000 to get to newtons. Okay, if it's in meters, convert your meters. If your area is given in meter squared, convert that meter squared to millimeter squared so that you have visually in megapascals. From megapascals, it's easy for you to move to gigapascals if the question entails that you leave your answer in gigapascals. Okay, so F is the instantaneous force load applied perpendicular to the specimen cross-section. Original cross-sectional area before any load is applied. Okay, so that is engineering stress. What is engineering strain? This is defined with epsilon. Okay, this E that looks like an E, it's actually epsilon. So epsilon is defined at any point in the test as LT minus L0 over L0. And then there's that delta. So this instantaneous length just basically means the length, it can be L1. It doesn't really have to be LT. So you have the original length. So you have the length that happened, isn't it, at the point of testing. So that would be your L1 minus L0, which is the initial length of your specimen, divided by initial length. So L1 minus L0 is the same as delta L. So you have delta L over L original or L initial. Same thing. So sometimes strain is also expressed as percentage in which the strain value is multiplied by 100%. Okay. Any questions so far before I continue? Are we moving on the same page? We'll continue?
We are following, madam.
All right, good. So we move to compression tests. So apply a load that squeezes the ends of the cylindrical specimen between two platens. This one, at least we've understood the compression. We know what compression looks like. And the specimen, pardon? Yes, please. Someone wanted to say something? Okay.
Madam, I wanted to ask,
Yes.
why is it that at necking, the load or the force tends to reduce? What causes that?
Sorry, I didn't get the question. Why is it at what?
At necking,
I can't get that.
the load starts to reduce.
Oh, necking. Why is it that the load starts to reduce at necking? Can someone answer that one?
Hello, madam.
Yes, how is it that at necking, when necking begins to happen, we read that the load begins to reduce?
Yes, that's my question, ma'am.
Yes, now I've moved the question to the class. Can we have someone who can respond to that question?
All right.
Okay, so you need to understand that at necking, what reduces is what? The cross-sectional area, right? So pressure is
Yes.
applied where? On the cross-sectional area. So with a reduction in the cross-sectional area, it means that also the force there begins to reduce. That's the understanding. At the point of necking there, where the necking is happening, okay, the cross-sectional area is reducing. So that reduction is what facilitates that decrease in force also in the tensile of stresses. You can move. Okay. Okay, so we move on. Oh, compression is, oh yeah, we understood. Okay, I've got a question for you also. If have we understood what compression is, we've seen how it works, isn't it? So with compression, what happens? Cross-sectional area, it increases, isn't it?
Yes, madam.
So meaning the object will become wider, right? The edge or the length will become smaller.
Smaller, yes.
Yeah, but the cross-section area will become, that's like a loaf of bread. What happened to it? Huh? Okay.
Yes, madam. All
right. So now, if this is the case, I would like to address, I hope we have people who drink wine here. I personally don't drink, but I want you to help me. This is your time to shine. All those that take alcohol. Oh, we have less than a minute. Okay, I'll ask in the next section, in the next session. But anyway, in a few seconds, why is it that when you shake a bottle of champagne or a bottle of wine under pressure, you buy a new bottle, then you shake it continuously, that bottle, what do you have now? You have that the cork stopper will just fly out, isn't it?
Yes, madam.
What can you explain what happens in terms of compression?